Okay, thanks. Yeah, so Sid told me to speak for whatever, 45 minutes, give an overview of kinetically constrained dynamics. And how these, originally classical ideas about slow relaxation, might have some bearing on a variety of quantum problems. So what I was going to do was to, try to cover briefly, the essentials and try to connect to what I think are interesting issues in quantum systems. So this is my plan. I wanted to talk first about the problem that originated the thinking, and that's the glass transition problem. So just the very basics of what the glass transition problem in classical many-body soft matter is, and then this is why kinetically constrained models, which are the models that furnish this idea of constrained dynamics. So then our second topic would be the basic classes of these models, so KCMs. So what are these classical models? And there are two classes. One is so-called facilitated spin models. There are two basic ones: the Fredriksson-Andersen. So I'll say what that is about. These are simple spin models that have constrained dynamics, and the East model. And the second, important class is that of constrained lattice gases. So I write here the kind of the plan so that we know where we are. And the third class, and then the third part is a different class of systems. Systems which don't have explicit constraints in the dynamics, but the constraints emerge effectively, and those are plaquette spin models. So here's the third part. And in a different color, I'm trying to say how this connects to current problems in quantum many-body. So facilitated models, relate to effective descriptions of operator spreading. And this is, work by Adam, relates to this. So there was even a paper today by Sarang, Golapannakrishnan, and others exactly on this. So what else? So they connect, of course, to quantum slow relaxation, let's say quasi-MBL. The possibility of having slow relaxation and something that looks like localization in the absence of disorder. And they also relate to work by Dima, Maxim, Slatko Papic, and co-workers on what they call quantum scars. The existence of these very long correlated states with very, very long correlations, again, that emerge through constraints. So this is a classical, and I think that connects to at least this set of ideas. And I want to mention plaquette spin models because this relates directly to the problem of fractons. In fact, not from the quantum information side, but from the more many-body side. The original fractal models were generalizations of these classical ones. So this is kind of my plan to speak about these three things, more or less. Not in a lot of detail, but I think it sets the scene for the things that I think are worth discussing. So what's a glass transition? Many of you know what this is about. It's the physics of essentially dense cold liquids. And it's the generic physics if you have classical many-body systems that have essentially excluded volume interactions, like you have in a liquid, you have molecules and they cannot occupy, they exclude each other, they cannot occupy the same position in space. And if you make it dense, like you would do experiments, let's say on colloids, or you cool them, you can do on liquids. Effectively, the effective density goes up. And if you have no quench disorder, just simple two-body interactions of the excluded volume kind, and you make the system dense, relaxation becomes slow. That's kind of obvious because you have particles blocking particles blocking particles. So if you want to relax, which is to move a particle away from its initial position, it needs the neighbor to move, and the neighbor needs the neighbor to move, and so on and so forth. And this collectiveness is what gives rise to slow down. So then, if one quantifies, calculates a correlation function, it's essentially quantifying how much particles have forgotten their initial conditions, and properly normalized goes from 1, where you remember everything about the initial condition, to 0, where you've relaxed. In a system that thermalizes, in the normal fluid state, this relaxes quickly, from 1 to 0, if I could draw it properly. And then when you cool it down, and these excluded volume interactions become more and more prominent, two things happen. Relaxation starts to become essentially two-step. So there is a separation of timescales, relatively fast. Part of the degrees of freedom forgets, about the initial conditions, but full thermalization, if you want, full ergodicity, forgetting completely about the initial conditions, takes longer. If you go colder, it takes longer still. This is usually in a logarithmic scale when you see these plots. And eventually, it takes so long that it reaches experimental timescale for observation. And that's what we define a glass. So this we call a glass. Material that does this we call a glass, not because it's undergone any, necessarily a phase transition of any kind. It hasn't had a phase transition to a solid state, just it takes too long to become ergodic, to be observed to become ergodic. So this is separation of timescales, and it's easy to understand. As you become denser, short scale motion, it can remain quick, and that gives you, partial relaxation, but longer scale motion that really makes you forget your initial conditions takes much longer. So then you measure timescales by the timescale associated to how long these curves take to relax, and then you plot it. And the thing that's making it slow is typically decreasing temperature or increasing density. So 1 over temperature growth. So if you plot it in that way, logarithm of the time scale, it grows. And it would keep growing if one could measure it. But in practice you can't. And this is a point where you stop. In convention, this is 100 seconds. That's how slow the relaxations of something we call a glass is. And the important thing is that the shape of this curve is what's called super Arrhenius. And that means that it's faster than the exponential of some number over temperature. So what this means is, because this is a thermal system, and relaxation is driven by the fact that you have thermal fluctuations. If this curve had been Arrhenius, exponential of inverse temperature, which is a straight line in this description, that would suggest that there is one kind of energy barrier that dominates the relaxation, that's fixed as a function of temperature. Because it's super Arrhenius, this means that in effect what's going on is there is complicated spectrum of relaxation. You already see it in this separation of timescales. And that's a characteristic of something whose relaxation is collective. So, slowing down, very, very fast growth of relaxation time. In experiments, the typical timescale for a liquid is picoseconds for relaxation time. And this goes to hundreds of seconds, minutes. So these are like 15 orders of magnitude or more. So it's very, very, very pronounced on a relatively short temperature range. So now, this wouldn't be surprising if there was a change in structure, but if you look at structure of glass-forming liquids, still here in the equilibrium, slow but thermalizing regime, the structure doesn't change. So there is no, there is no growth of structural correlations that one can see, but the dynamics shoots up. So that's the first pass. A slowdown, no change in structure. And the other important characteristic is what's called dynamic heterogeneity. I could show you some movies, but I decided to do it on the board till the end. Let's see if this is clear. So if one looks at the material, what I'm trying to draw is a movie now, in terms of stills. So this is space, for a liquid. And if one plotted, so this is the average correlation. It is a correlation that's local relaxation averaged over the whole sample. So if one resolves this spatially, such that projects the evolution of an equilibrium trajectory back on space, where each point here is the local value of this correlation function, which is saying locally have I relaxed or not. So this is something that goes from all white, or all black in this color, to all white, where black is 1, the beginning, and white is 0, the end, eventually. And it's just a statement that the system will completely forget its initial conditions, will thermalize. And the question, how does it do so? As a function of time, time is going that way. And if you look at movies of this kind, you can quantify it. People do experiments. They can do it, observe it, explicitly with colloids, or in liquids you have to do other kinds of experiments. What you see is that the emergence of relaxation going from black to white is not homogeneous. This is not transforming slowly from black to white through various shades of gray. So these various shades of gray are the values of this overall function. It does so in a heterogeneous way. There might be some initial relaxation there, and some relaxation there, and some relaxation there, and some relaxation there, which is saying molecules here have relaxed, molecules here have relaxed, molecules here have not relaxed, have not forgotten the initial conditions. And then from there, those relaxation domains start to grow, and eventually they cover the whole system, and you've relaxed. So two things occur. There is the emergence of very appreciable correlation lengths in the dynamics, and these lengths are much, much larger. What I said were totally uninteresting static correlations lengths. There is no static ordering, but there seems to be some kind of mesoscopic ordering in the dynamics, and it's called dynamic heterogeneity. And the slower the system is, the larger these dynamical correlations, and the more fluctuating these relaxation patterns. Okay? So this is a final characteristic. So statics is not very interesting, but dynamics is. Which is not the usual setting in classical condensed matter, when usually statics and dynamics go hand in hand, but this is not the case here. So this is the basic physics of gases. And the question is, what are the basic physical ingredients that describe this? Slow relaxation without any interesting change in structure. So you have to, theoretically you can think in two ways. I'll make two sketches. This one that one sees a lot, configuration versus something that is like free energy, whatever that really means in this picture. I didn't want to make it as symmetric as it looks. They're random landscapes. And it's kind of the intuition from problems which have quench disorder, and say, well, some free energy landscape, configurational landscape is, looks disordered, and there's, distribution of individual states is interesting. That might lead to some, change in the thermodynamics, and that leads, therefore, to this interesting dynamics. That's one perspective.
So in this picture, right, so if one takes some reasonable model with local interactions, whether it's a spin glass or maybe some other model, so what is actually known about statistics of this minima, and how tall is the barrier?
Well, so there's been, for 20, 30 years, a lot of work coming from spin glasses on these kind of problems. And these are problems that are easier to solve in mean field.
You mean this P-spin?
So that's our model of spin glasses that people who think that this is a correct picture would also think as an effective, reasonable starting point for structural glasses which don't have, explicit quench disorder. In mean field, one can calculate exactly some of that statistics. Even I've written papers on that. But nevertheless, that's not the picture I certainly it's a correct perspective for spin glasses to start from. I don't think it is the one for glasses. That's not the one I want to emphasize. And it's not the one that connects to these kind of problems.
But is it even believed that these concepts that apply to the mean field spin glasses, that they actually apply to short range spin glasses as well? I've never even heard a statement like that.
So I can talk a lot about the glass wars. So what I'm trying to emphasize is that this is the basic perspective. Is the problem fundamentally thermodynamic, where there is some underlying ordering that's random because of some effective randomness, and the thermodynamics leads to the dynamics, or is the problem fundamentally dynamical, or it's not useful to think thermodynamically, one has to think dynamically. The phenomenology, to my eyes, points to this, especially this behavior. Because the dynamics looked at this level is very, very far first from mean field, and it's telling you that what's interesting is trajectories, not statics. Well, I don't even have a picture for the statics. People don't, we don't agree, and there are different views. And it's not obvious that these perspectives are necessarily completely incompatible, but they are almost orthogonal from the starting point. So this is the idea I'm trying to emphasize. If this is configuration space, what the phenomenology is telling us is not necessarily that configurations are special in any sense. If I think of hard spheres, which is the essential model for liquids, all allowed configurations are essentially the same. It's really that at high densities, low temperatures, it's difficult to connect them. It's the pathways. So these configurations might look like they are close by, but the pathway that they're allowed to take to connect them is complicated. So if you want, one can even try to quantify this kind of the metric structure of configuration space allowed by the dynamics. Yeah. So that's the idea. So this is the essential idea. So what I try to furnish is these with models that are very simple and capture this kind of intuition. And these are KCMs. So that brings me to part 2. So what are kinetically constrained models? So this idea, the essential ideas go back almost to the late 70s, and even back to Phil Anderson, who expressed in a paragraph in some lectures the essential ideas. But the first explicit model was written by Fredriksson and Andersen in '84. So what's a KCM? The KCM is the following: what's a kinetically constrained model? It exploits the following ideas. I'll try to motivate it with this excluded volume. So imagine I have a particle here. For simplicity, I will put my particles on a triangular lattice, which is a nice lattice to describe excluded volume. And this is like a lattice gas. So this particle would like to hop here. So I would like to have a transition from a situation where that particle is there and that's a vacancy to a situation where the particle is here and that's the vacancy, and backwards. Okay? And I'm going to call this A and that B. So there is a rate A going to B, and there is another rate B going to A. And I'm thinking about stochastic dynamics, which is these elementary rates for hopping. Yeah. So, for those of you who've ever done simulations, one could do like a Monte Carlo here, of this. And generically in Monte Carlo, you say, well, I go from A to B, and there is some term, if you use the Metropolis rule, which is minimum of 1 of e to the minus beta, the difference in energies A and B, where this delta is the difference between the energies of A and B. Now, this is the usual rate that one uses. If this is a lattice gas, this is the same, but generically this rate is the asymmetric part of the rate, in the sense that the reverse transition will have a different value here because the changes in energy, are the opposite. And usually this is multiplied by some overall rate, and this is the symmetric part, in the sense that this rate is the same going forward and going back if you want to obey detailed balance. So this is the kind of dynamics we're thinking. But because this is symmetric, so it's a function of the beginning and the end, and it's the same as if you invert it. No one prevents us from writing this rate as a function of the state and of the part of the state that doesn't change, and it stays symmetric. Yeah, because if we take the ratio, it's the same going forwards and going back, and detailed balance is controlled by this. So this dynamics, modulo ergodicity, blah, 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 goes to stationarity controlled by the asymmetric part. How fast it does so also depends on the symmetric part. And this is the kinetic constraint. So this is a kinetic, I hope you can see from everywhere. So this is a kinetic constraint. So kinetically constrained dynamics explicitly plays with these in the definition of the dynamics. Yeah? So what this is saying is, this we know from Monte Carlo, one can have many different dynamics going to the same thermodynamics, and one can exploit these to define local dynamical rules that have some physics in here. And the example I want to show is that how can we motivate excluded volume interactions? We can say the following. If these are like spheres going from there to there, which are the only two particles that change, could depend in rate on the neighbors which would block it. This is kind of the very elementary thinking. So this is a function such that if this particle is not there, this is allowed, forwards or back, because it's symmetric. If that particle is there, it's not allowed. What I mean is, so let's make it small. So a transition using this, which is this forwards and back, is allowed because there's no particle blocking it. This gamma is 1 for forwards and backwards, but a transition which is like this, going there where this particle is present. So this one is okay, but this one is not. Yep. And a lattice gas with these dynamics has the same stationary state, which is trivial, of a normal lattice gas, but the dynamics depends very, very strongly on density. Because the denser the system is, the more of these non-allowed transitions there are, and the more complicated pathways the system has to take. Okay, so it's just to say that this is a relatively simple way to incorporate these two ideas of decoupling the thermodynamics from the dynamics, and because the thermodynamics is determined by the symmetric part and the dynamics is determined by everything. Okay? And I've done it in a way that tries to motivate excluded volume. So one can construct lattice gas models, and this is a constrained lattice gas example. Lattice gas models where the rates are constrained that mimic excluded volume interactions. And then one can ask, is that good kind of model to think about slow glassy dynamics? And the answer is yes, but first I want to so I'll leave this constrained lattice gas for in 5-10 minutes from now. So let me discuss first, because they're slightly simpler, facilitated models, facilitated spin models. And interact me or ask me questions. All of this, each of the things I say can be expanded. I mean, have been studied for by myself for many years, a number of years. So, discuss first the Fredriksson-Anderson model. It's from the 80s, 84. So this is the simplest facilitated. This is the simplest kinetically constrained model. So it's a spin model on a lattice, so you have one-dimensional lattice. And the dynamics is such that you go to the equilibrium of a non-interacting energy function. So the energy of the problem is just the sum of the up spins. So you have Ising spins up and down on each side of the lattice. Let me call them zeros and ones. And the stationary state is non-interacting because the stationary probability is e to the minus beta e. And the energy function is just counting how many spins there are. Okay, so the equilibrium, the thermodynamics of this problem will, by construction, have zero correlation functions because the only thing that matters is expectation value of that operator that we'll be interested in low temperature. So this goes as e to the minus beta j, but correlation functions for ni different from j are just n squared. Okay, so the thermodynamics by construction will be trivial. So now we're thinking of the dynamics, and to make clear what I mean, this is stochastic dynamics. So let me write the master equation. So the master equation is a probability vector that evolves with some generator, Markov generator, I'm calling W, applied to that probability vector. Okay, so it's just you choose a basis, which are the configurations, and the vector that you build is the elements of the components of this vector are the probabilities of each configuration, and the probability is given by the probability of some configuration is e to the minus beta the energy over the partition sum. Okay, in equilibrium. So one wants a dynamics that flows to this equilibrium, and that I will write the dynamics that incorporates incorporates a constraint. So let me write the dynamical rules, and later on I will write the actual operator. So the idea is the following. Usually if you have a spin problem and you want to go to that equilibrium, you say, well, I'll define a dynamics that flips spins up and down with certain probabilities. Yeah? And by detail balance, the ratio of the probabilities has to be compatible with that. Yeah? And the ratio of the equilibrium probability. So if I have a downspin and spins cost energy, I call epsilon, where epsilon is e to the minus beta j. So epsilon at some positive temperature, epsilon. So the rate to flip up spins is smaller than the rate to flip them down because they cost energy. A dynamics of this kind, of course, will be flipping spins independently, and overall it will flow to that distribution. But I will incorporate a constraint. I will say the following. This rate is allowed. So this rate is allowed if the neighboring spin is up. It's not changing. So this is this function I'm putting here. So the ratio is, the asymmetric part guarantees equilibrium. But now the rate will be, the allowed transitions will be the following. If the spin on the left is up, that spin facilitates to the east. So that spin neighboring next to a 0 allows it to flip up, or if it's that spin next to a 1 allows it to flip down. Or let me draw it like this with the same rate. A spin that's up facilitates to the west, so this helps that one to flip down. Or up conversely. And what's not allowed is a 1 flipping to a 0 or vice versa. So this is allowed, this is allowed, this is not allowed. So spins cannot flip is surrounded by an unexcited spins. Okay? So this realizes this. It realizes this state-dependent rate, because the spins that determine the rate do not change, but tell you whether that rate is 1 or 0. And the rest is given by the energy difference. And that's a kinetic constraint. So now, this goes to that equilibrium. That equilibrium is trivial, but this dynamics is certainly non-trivial. And I'll show you why. And it's non-trivial, and you can already see what kind of conflict there is. To have any local dynamics, any change, you need excited spins. At low temperatures, excited spins, on average, are less likely. So low temperature wants to have fewer up spins, but fewer up spins means less dynamics, and the system therefore has a conflict. He tries to reduce spins going to low temperatures. Up excited spin is going to low temperatures, but without excited spins, he cannot move. So what's going on? So let's think a little bit. So another way of drawing this, these transitions is if I have an up spin, which I draw as a line, I can branch into two. And because this is reversible, if I have two, they can coalesce into one. If I put these together, two of these together gives me a hopping, and because this can be done in both directions, what I have is I have diffusion, which I'll draw as a wiggly line of excited spins, and then they can branch and they can coalesce with certain rates that come out from here. So if I draw a trajectory now, so now I draw a trajectory, space and time, and let's say low temperature, so I don't have many of those, many excited spins, which I draw as dots. These spins effectively diffuse. If they come together, they can coalesce, not annihilate, but coalesce. They might branch out, and then others coalesce here and branch out, and so on and so forth. So now this looks like an equilibrium trajectory. I've drawn it in such a way that it's not very clear. If I flipped it, you wouldn't be able to tell in which time direction is going. So I started from a typical equilibrium configuration, and I evolve it. If this is in equilibrium, any cut is non-interacting because any cut is a configuration of the equilibrium measure which has zero correlation length. So every cut is statistically trivial, but the trajectories are not. So static properties are trivial, but the trajectory clearly is not. It's branching, coalescing polymers. Okay? So that's the first statement. Trajectories are non-trivial.
Sorry, can you repeat why each car is trivial? Can you repeat that statement?
So these dynamics respects detail balance with respect to this trivial distribution. If I choose an initial configuration from this distribution, statistically this evolves and it's preserving the distribution. Okay. And that's why the trajectory doesn't looks time symmetric because I'm in equilibrium. Now, just to address a little bit of that question. Now, this is an equilibrium problem, but I can start away from equilibrium. Imagine I only have an excitation there, and I go to a larger scale, longer time. So how do the typical trajectory look, that space? Well, because of the dynamical rules, if there are no excitations here, nothing can happen. Things can only happen next to the excitation. So what happens, this excitation starts to develop more excitations. On a finer scale, it looks like this. But on a broader scale, what there is a front that propagates ballistically. This can be proven. So you have, propagates ballistically, and eventually it covers everything. And by the way, these are the pictures that are being used for effective operator growth. And in fact, these effective models are FA-like models. And the issue there is that if the operator is in a one has to assign, the kind of operator, operators to these ones and zeros, but the rules of how operators can spread lead to this. I want to say two things, and then try to motivate later. So if I didn't tell you what this is space and time, what you see here is you see two phases. You see a dense phase, I will call it active, because lots of motion is going on here. You have lots of motion because of these excitations. And here you have a phase where nothing's happening, so this one I call it inactive. So I have two different phases. The two different phases have different densities of motion. Lots of motion here, very little motion there, a well-defined interface. This is first-order physics, first-order coexistence in trajectories. Not in configuration, but in trajectories. So inside here we have essentially the equilibrium phase, and here we have the inactive phase. And first-order coexistence.
The ballistic thing comes from the branching of the walks?
Sorry?
The ballistic thing comes from the branching of the walks?
So because they branch, eventually this front is ballistic.
How does it depend on epsilon?
Sorry?
How does it depend on epsilon?
So the slope, that's the speed, will depend on the temperature. I can come back to this. I will try to come back to this later. Okay? So when one studies slow dynamics in the equilibrium state, one focuses on this. Yeah, if you're thinking of this spreading, you're focusing on this. The underlying physics is this one of these first-order coexistence in trajectories. It's very, very clear here. The second thing I want to say is that the inactive phase is empty. The active phase is much more interesting that I've drawn it here because it has fluctuations, that I'm going to call space-time bubbles. Even if the overall phase is active, is dense in activity, it has mesoscopic fluctuations of the empty phase. I will come back to this. So I'm trying to emphasize two things. As a consequence of constraints, one has rich trajectories, trivial thermodynamics. One has this anticipating coexistence of phases. And one of the two phases is completely empty. The phase which is non-empty has interesting mesoscopic fluctuations. So.
Sorry, what do you mean by first order coexisting trajectory? So what is first order?
If I had time, I would try to describe it. So what I mean is that so there is an ensemble of trajectories, all the possible stochastic trajectories of these dynamics. And this ensemble of trajectories is essentially composed of two phases. One which is a phase which is empty. Yeah, that's clear because if I start with everything that's empty, I'm simplifying, that's a stable dynamical phase. And if I start with something that's not fully empty, that flows into the other phase. Okay? If there wasn't a constraint, how do I go from there to there? I just flip the spins everywhere, and then I fill it up. It's really the constraint that's giving you this phase separation. So I have about 10 minutes, and there are a couple of several other things I want to say. So you're chairing, right? So you stop me when you want.
I think there are good questions going through. So.
Oh, okay. So now let's talk about the East model. The East model is the same, except facilitation is only to the east. So this can help, this facilitates, the constraint is such that this is the only transition that's allowed. Okay? It's a little bit artificial because the system looks only in one direction and so on. But what happens? The constraint is stronger. Because it's stronger, the dynamics will fluctuate more and will end up being slower. And that's something I want to show. The second thing is that this process of the effective hopping cannot occur because effective hopping means, combining, two of these facilitated events to the left and to the right, to the east and to the west. I need the east and west facilitation to hop. So if I don't have that, this one can help this one to get excited, for example, or this one can help that one to get excited, but then this one cannot help that one to get de-excited, and therefore there is no effective hopping. Constraint is stronger, and I'll give you the answer, and this is an important result in classes. So what's happening is the following. At low temperatures, we have few excitations and lots of zeros. So a typical region in a low temperature configuration looks like this. And in equilibrium, there is some distance between these two, which is e to the beta j. That's equilibrium distance at low temperatures between two excitations. Okay? But imagine we have, that would be this is the equilibrium distance, Lec. So I can explain what it is, but excitations, while here are diffusive, here cannot diffuse. All I can do is I can promote excitations next and promote excitations next until I get here and I'm able to annihilate that one, if that's what I want to do. I want to relax the spin. I have to come from the nearest one to the to the west in this case. So the nearest to the left is the one that will help me relax. I could turn every spin on. That would give me an energy barrier I need to cross that scales with system size. There is a more clever way of doing this because I don't need to keep every spin on. The energy barrier depends on length and it's logarithmic in length. It's really log base 2, and I can explain how this is obtained. But the key thing I want to say is that this is the energy barrier to relax a spin at distance L. So what's the scaling law for the relaxation? So one needs to activate an energy barrier of size L divided by temperature, but that L is logarithmic, and I'm skipping lots of the constants. So the scaling law is that the time scale associated to length L goes as a power of the length to a power that's the inverse of temperature. So this problem is diffusive, so the scaling law here is L squared. So here you have a scaling law that goes as L to the inverse temperature. So the scaling exponent gets stiffer and stiffer and stiffer the lower the temperature. So if I put everything together and I calculate what's the typical relaxation time, is a relaxation time associated to the equilibrium length. So that's the equilibrium length, typical distance between excitations is exponential in beta j. If you raise that to the power 1 over t, what you get is e to the sum number over t squared. Okay? So one makes the constraint a little bit stronger. These statements about complexity of trajectories, spreading of initial excitations remain. But what happens is that dynamics is slower and it's super Arrhenius. Yeah? So this super Arrhenius looks a little bit like this. I could show you pictures saying this is a pretty good scaling law for the phenomenology, by the way. So it's a super simple problem that, due to the constraints leads to this very, very slow relaxation. So, I have a few more minutes. There are a couple of things I want to say. So I said that, how does this connect to quantum problems? Or what implications are there on quantum problems? Let me write this generator. So for the East model. So how does it look? I want to flip spins at site I. And let's forget about the energetics. Let's concentrate on the properties of what the constraint part of the dynamics does.
Sorry, okay.
Yeah.
So in that case, there was a diverging length scale which was associated with the very slow relaxation.
Okay.
Not like what you were describing.
No, there is no growing correlation length. There is an increasing distance given by a decreasing density. So the density of excitations is going down, but in the stationary, in the equilibrium state, there is no correlation still between excitations. If an excitation is here, it doesn't affect the probability of the excitation being next to it. Is that clear? Mm-hmm. So this and that problem have a trivial stationary state still. And of course, that the quantity that's controlling whether you're fast or slow is temperature, and through temperature the density of these ones. Yeah? Okay. So let me write this operator. I want to leave a bit of space there. So, basically what's going on is locally I want to flip a spin. And the Markov generator that does this is sigma x, that's the term that flips the spin, and 1 is the associated escape rate. Yeah, Markov operators are always like this, have a positive off diagonal that gives you the rates of transitions, and a negative off diagonal that gives you the escape rates, and the columns add up to 0. Yeah. But the rate is not constant, it's a function of the neighbor, ni minus 1, and this is summed over all. Okay, so this is the operator. Yeah? I'm going to say two things. First of all, I wrote it as a Markov operator, and one could say, let me just call it minus a Hamiltonian. Yeah? And the second thing I'm going to say is that this Hamiltonian, as it stands here, is at a Rorschach-Iverson point. In the sense that the ground state of this Hamiltonian is frustration-free, and the ground state is nodeless and is given by an equilibrium probability. It's essentially given by this equilibrium probability, because we know it's a Markov generator that goes there. So if we think of that as a Hamiltonian, the ground state is the eigenstate of the largest eigenvalue of the Markov generator, and therefore is the ground state of this operator. And that is given just by that probability. So it's at a Rorschach-Iverson point. So now, and the way I've written it, let me see if I have that here. So let me deform this operator. So let me deform it away from being a stochastic operator by a parameter I'm going to call lambda. So here I put lambda, 1 minus lambda. So now lambda equal to 1/2 is the Roxar-Kivelson point. So now let's think of, you want me to stop?
No, I think keep going for the moment.
Oh, you stop me, okay? So let me try to come back to this coexistence. So now, if you look at this operator, it's a sum of the product of two terms, the constraint and the usual unconstrained transition, local transition operator. So how do I get the largest, the eigenstate associated to the largest eigenvalue is 0? How do I make this operator 0? I can make it in two ways. I can either have a state where the constraints are all unsatisfied, that would be the all zeros, a configuration that's all 0 is an eigenstate. And it's like a trivial eigenstate. If I start from all zeros, I cannot move. Or I can annihilate all of these terms, and that's the equilibrium state. So the other one is the equilibrium state. So basically what happens is that if I look at this operator, it's block diagonal. It's reducible. It has one block, which is the constraint is never satisfied, and then it has all the other configurations in a block that's connected dynamically. Okay? So that's the first statement. But the fact that it has a product structure is important, because locally I can annihilate this, which is be local in the local region in equilibrium, or I can annihilate the constraint. If the constraints are all annihilated, I'm trivially disconnected. There's no dynamics associated to this. However, the existence of this state is what gives this class of problems in general all its interesting features. And the reason is the following. All other states are connected, but among the states that are connected, so this matrix is non-trivial, there are ones, most of them, which have a finite density of ones, finite density of excitations. So that means that all of these states, the typical distances that one needs to traverse to connect them, does not scale with the system size. And then there are states which have finite density. And then states which have a vanishing density, which is not saying that they have 0 excitations, but it's a density that goes to 0 in the thermodynamic limit. Okay? So now we have an operator that has this structure. So now let's think a little bit what happens. If I start from a configuration here, I can connect it dynamically. But because the time it takes to connect these two configurations that lie on this part of this subspace depends on how far apart the excitations are. So the ones that lie here have finite times that connect them, while the ones that are here have times which will diverge in the thermodynamic limit. So they are dynamically connected, but the times grow and grow and grow and grow. So eventually, I don't even know how to draw this, so eventually the matrix elements here that connect these states to those states, these go to 0 in the limit of L going to infinity. Yeah? So what this is saying is that if I start from states, so if I start from states that have vanishing, a finite number of excitations in a very large system size, it takes very, very long to escape from them. And if I start from the others, it doesn't take long and they connect quickly. So this is the essence of this phase transition. Let me just prove the transition quickly, and then I haven't said anything quantum yet, and I will say it very, very quickly. Okay, so this was this operator, which is the original dynamical operator. How do I probe this phase transition? So I deform the operator in this way, away from the Roxar-Kivelson point. if lambda is larger, so let me now draw the ground state, or minus the ground state of the Hamiltonian, of this Hamiltonian, as a function of lambda, or essentially lambda, and this is lambda 1/2 is this point. So the ground state of this operator at finite size is 0 at lambda equal 1/2, because that's the stationary state, and it's something else that's not quite, it's just the ground state of this deformed operator, and it bends very quickly, and this bending becomes sharper and sharper with system size, and eventually it becomes singular. And if you look at the derivative of this, minus the derivative with respect to the log of lambda I will plot, so of if I did it properly, it tends to a first order phase transition on either side of Roxar-Kivelson point. So what this is saying is that in the thermodynamic limit, so this is, the system is finite, this gets rounded and gets sharper and sharper, eventually it's a first order transition. And the physical meaning is that the ensemble of trajectories, and this is what this is describing, at the dynamics, at the point where the dynamics is taking place, is at first order coexistence between a dynamics that has finite activity and one that has zero activity. These two phases I was talking about before. Okay, so that's the glass part. Let me just say one or two things about the quantum, but if you see it, tell me if...
Yeah, maybe you just do the quantum method.
I do very quickly the quantum. So now, inspired by this, one can say, well, I've been describing stochastic dynamics, coming from glasses, and this idea that slowness and complicated relaxation and so on emerges from constraints. Let's say that now, and the other thing is that these generators of stochastic dynamics have some interesting structure in the ground states and in the low-lying spectrum.
Isn't the first order phase transition its continuity in energy, or like level crossing?
So here is a discontinuity, is a singularity in the largest in the probability associated to the largest eigenstate of the dynamics. If this was a Hamiltonian, that's what would be.
So it's a level crossing, or is it a jump in the... So it's basically a level crossing.
So there is level repulsion at finite size, and it becomes smaller and smaller and smaller. This is what you have to take the thermodynamic limit.
Okay.
So this is smooth and smooth and smooth by level repulsion, if you want, and only in the limit it breaks up. This is what I was trying to emphasize here. That this matrix is connected, but the connection becomes weaker and weaker and weaker as system size goes to infinity. Now, let's say the following. Now let's imagine I take a Hamiltonian of this kind. That's the first thing I want to say. Yeah. So now I take a Hamiltonian of this kind, which in general has an off-diagonal part that I will call T, and a diagonal part I will call V, and this parameter lambda that balances between the two, and at lambda equal 1/2, it's at the Roxar-Kivelson point. So that's the constraint. The presence of the constraint means something for the quantum dynamics. I'll give you an example. I'll try to connect another couple of things. So now what we do is we do coherent evolution with a Hamiltonian of this kind. Yeah, T sin A. So no longer a classical problem. The classical problem has given this idea of the constraints. What the constraints do is, restrict the connection between configurations. Let me see if I'll show you one graph to show what I mean by this. What I'm going to implement is, the example is, this constrained lattice gas. How does this? Yeah. Okay, let's see how this. So which one do I need to press? Oh, there you go. Let me show you just quickly what kind of thing can happen. I'm saying, do constraints lead to slow quantum relaxation? So now I'm just I'm evolving coherently with a Hamiltonian. This Hamiltonian is inspired by the classical problem. It's a fully quantum problem. So let's imagine like before we have this triangular lattice, and we have this kind of a lattice gas, so single occupancy, and the particles would like to hop. So sorry, what's this inbox thing? Okay. Sorry, I don't know what that inbox is. So, but the inbox points to the hopping term. Yeah, it's convenient. And the other term, forget about lambda for a second. The other term is a corresponding diagonal term. In the quantum case, it's a potential energy. In the original classical case, was essentially the escape rate. So this is hopping with some particular interactions. But all of that, each of those parentheses that give you a hopping term, back and forth, is multiplied by a constraint. I don't write the constraint, but it's the one I said before. So it's drawn here. This particle can move there because the common neighbor is empty. There is space to go through, quote unquote. But this particle cannot come here, even if this one is empty, because that one blocks it. So this. I'm not saying what can be done. So in this particular one, this one can go there because at least one of the common neighbors is empty, but this one has both neighbors blocking it. Yeah. So this is what it is. So it's like originally the same rule on a triangular lattice, but one cannot simulate a 2D triangular lattice. It's just it's like a slice where everything else is full. Okay. So this is hopping with that particular constraint. So now let's see what the relaxation does. First of all, one can discuss it. This problem obeys ETH. Yeah? So this will thermalize eventually. Secondly, if I apply this dynamical rule to a classical problem, it wouldn't be very glassy. So these are very, this would be a renormalized lattice gas. Everything would be diffusive, simply. I can explain why maybe in a second. But let's now run coherent dynamics and kind of consider what happens to the relaxation, to the thermalization by measuring density correlations properly scaled so that they start from 1 and they thermalize to 0. Yeah? And what you see is that when lambda is larger than Roxar-Kivelson, so the kinetic term is dominating, all initial product states, so it's sampling the identity, the infinite temperature state, all of them relax relatively quickly. The black line is the average. On average, the infinite temperature average of these correlators goes down quickly. But conversely, on the other side, there's a very large fluctuation depending on initial conditions. And many initial conditions are extremely slow. This is a logarithmic scale in time. They decay only partially, like the separation of timescales of kind of glassy problems. I would call this metastable. It's metastable in the sense that some people would call it, pre-thermalization maybe. But this is metastable. It only relaxes partially. And only at longer times it relaxes fully. Yeah.
So what is y-axis here?
Oh, sorry. So this axis is this normalized to go from 1 to 0. Okay?
Okay, because actually relaxation, 10 to the 4 is also not a small time scale for the relaxation. If you speak about whatever model with 20 sides and macroscopic energy unit 1, right? Or is there something? I agree that the second relaxation is much more spectacular, is much slower, but the original one is
okay. So the rate for relaxation. The rate for relaxation here is the same as the one that takes you to the plateau there, and that's essentially given by the rate by lambda squared. And it's a much, much steeper function of lambda for this relaxation. I think I have a graph afterwards. We can discuss the details, okay? All I'm trying to emphasize is this distinction, moving at either side of the Roxar-Kivelson point. Yeah. Remember, a Hamiltonian of this kind, because of the constraint, has some interesting structure in the ground state. I'm not making any statement about the excited states. I'm running dynamics, and this is what I get. And what else? So let's see. What's the distinction?
What the last sentence you said? It's not about excited states?
No. I cannot make any statement about excited states. I made some actually exact statements about the ground state. The ground state has a first order transition.
You're just saying the initial state here was not just the product initial state.
States are all product states, initial states. I have no idea how the spectrum looks in the excited states. Yeah.
You have a rule of thumb which determines which initial states end up having a plateau?
Yeah, thanks.
Okay, yeah.
It's one I prepared earlier. So, that's the whole point. There is a distinction between initial states. So what's going on? And we can go through the details. So first of all, that constraint in this case does something interesting at high densities, because at high densities it prevents many of these connections.
So what you've written there is an autocorrelator.
Yes.
The states you start out with, they're not eigenstates of the Hamiltonian. So
yes.
What you plot is, do you evolve both the operator and the state when you make these plots?
Okay, let's look at this. So I start from product states. So basically I'm summing the expectation value.
The expectation value, is that in the initial state always? And that's what I'm asking.
Yes. And it's simple because the initial state is a product state, so this part is...
It's kind of a weird thing to look at, though.
Okay. I understand. I'm trying to emphasize and connect with something glassy later. Okay, but I think it's undeniable it goes from fast to slow. Okay. How does it do so? This was, Kurt's question. So this is an initial state that's slow, this is an initial state that's fast. And I can describe what's going on. But basically what's happening is high density, as big as we can do it. I think we can do a bit bigger, but high density, everything filled. These are the vacancies. And the vacancies can, what can happen to vacancies? The vacancies can be in pairs or larger, or can be isolated. Okay, so here we have 4 vacancies in 2 pairs, and in the other one 4 vacancies into 1 pair and 2 isolated ones. So what happens is that vacancies can diffuse effectively, and we can discuss the rule, because this one has 1 free neighbor, so this one can move there, or let's see, this one can move there, so the vacancy tumbles, and then this one can move there, and the vacancy tumbles again. So effectively, they can diffuse. And we're in the smaller than, lambda, in lambda small limit, so one can treat the hopping as a perturbation. Yeah? Of course, they are slightly, off resonance, the states that are connected by the vacancy hopping, but that dresses and that gives you a diffusion constant for the vacancies. So pairs of vacancies. So dimers diffuse freely with a rate that goes as lambda squared, someone you asked. Okay? So then, dimers diffuse freely and dimers diffuse freely. So if I have a configuration like this one, I decay with lambda squared relatively quickly. But isolated vacancies, there's no motion here because particles are completely blocked. Yeah? So the dimer has to move, but when the dimer hits an isolated vacancy, the changes in energies, if you work it out from that, are much larger. Yeah? So the constraint prevents the configurations, and the configurations it connects start to take you more and more, take you away from resonance. So effectively what happens is that these can move a bit until it hits these walls. That's the initial relaxation. Yeah? And it takes much longer to penetrate those walls and keep going. And it's slow because what it basically does, it kicks this ball one side, and then it has to kick it again, and then it has to kick it again, and we can discuss that. So, strong dependence on initial conditions. And if one thinks of a very large system at high densities, there will be regions of the large system that have fluctuations, local fluctuations that look like this.
Sorry, I have a question about this, because so you have the constraints which is sitting in the C, right? But then there is also or you are running out of time.
No, now I have I've just used 4 minutes.
So should I?
No, I went past. Sorry. Yeah.
Perhaps I should postpone my question.
Maybe how much you have 4 minutes to go?
No, I was just joking. My clock went round. Sorry.
Fine, but do you want to continue and finish, or do you
I can finish after this. I wanted to show one more thing, and then we can discuss.
Show one more thing.
I want to show one more thing. I said, so this is low relaxation. Slow relaxation due to constraints. Yeah? And what the role that the constraints play here is stronger than the classical case, because not only they prevent pathways, they make the pathways complicated, but as you go along those pathways, you go further and further away from resonance. It's much stronger, the effect, than classically. But just with constraints, coherent dynamics can be slow. If the constraint is stronger, this could keep going and going numerically, and you think that you're in an MBL phase. Probably not, but the time is too long. Again, like in a glass. And the final thing I'm saying is that if things are slow due to constraints or local interactions like in liquids, the slower you are, the more heterogeneous the relaxation. And that's indeed what we see. Yeah? And some people think that this is kind of a obvious statement. We discuss whether this is obvious or not. I really want to emphasize it. So now, this is just an example of what I'm calling heterogeneous entanglement. This, again, this initial state that was slow. And remember, the idea is that the dimer moves fast, but the dimer finds it very hard to penetrate the region where there are monomers. Yeah? So one starts from a completely product state. And this product state is, among other things, a product state from the left and the right. So the left and the right is the initial product state, and times the right initial product state. And then you run dynamics. And the first stage of the dynamics is the motion of this one, this actual data. So this moves about. And then this gets entangled. So you entangle the region that's relaxing fast. But it's still a product state with essentially the initial state. So now there's been relaxation on the left, because that's the region that can move fast. There's been no relaxation on the right. And the entanglement has not entangled this part with that part. And then finally, only at very, very long times, everything gets entangled. And that's a longer time. So slow dynamics, a consequence in this case of constraints, is related to locally fluctuating dynamics and heterogeneous dynamics. And I'm claiming that this, which in the quantum case has a bearing on entanglement, is essentially what one says, essentially the same kind of principle that one sees in a classical problem, where if you are slow, relaxation is highly heterogeneous in space. So I think this concept is important. The slow dynamics has to be connected with heterogeneous entanglement. And if one makes a picture of the entanglement field, the kind of thing that I've seen initially from you, rather than progressing as just a simple front, it's at intermediate times, it's heterogeneous as well. There are regions where it's zero, and there are regions where it's very high. And it can be essentially quantified from a picture like that. So, okay, there are a couple of other things, and I'll finish. I haven't talked about fractons, but there is a class of models that connect to that, and it also, these kind of ideas also have some connections with the scars. But sorry, I'll stop there.
Thanks.
Okay.
So I just, as long as it's on the blackboard still, because there are obvious constraints that are sitting in the C, right?
Yeah.
But then there is also, and I thought that's what you wanted to emphasize, that the lack of resonances brings additional constraints. So in particular, I mean, it's very visible on this picture that of all the allowed transitions that you are drawing there, actually all but one is, I think, of resonance, because it's only, you see, the resonant transitions here are the ones that do not change the number of neighbors, of occupied neighbors, I guess.
Yes.
Right. Because only for, right? Because, so for example, if you take the arrow, if you... Yeah, but so I just want to first see whether I understand it well. So if the lower guy moves to the right, that is an off-resonant, right? Because the potential term is different by one. And lambda is small, so that's off-resonant. Okay, so it's clear that the model is much more constrained in the end. The effective kinetically constrained model that it corresponds to is more constrained than what is sitting in the C.
Yes.
However, and now we come, sorry, to my question, I don't see that in your results. I mean...
Well, if I had shown you, if I had run classical dynamics with these rules, then I always get something like this. I don't get this plateau. What happens? Classically, the dimers are not bounced off, because classically you don't care about off resonance. You only care whether you can move it or not. So this guy hits that one, and then keeps going. So at the end, I just have dimers that diffuse. So this problem is diffusive classically. This is exactly what you're saying. Quantum mechanically brings the extra constraint of the off resonance. And why are these off resonances? Because of the constraint.
So the constraint will be here that basically the dimer cannot pass the monomer.
Exactly.
Right? Or they cannot.
It has to wait longer to kick it one step, and then it has to wait longer to kick it another step. Yeah.
So actually, I kind of have a question about the energy landscape, because we are back to discussing energy landscape somehow, and there was this, idea that energy landscape with broad barriers, right, is quantum mechanics doesn't help you and actually gets slowed down, and with very spiky and sharp barriers, you can somehow effectively tunnel. So that seems to be more in this broad barrier case.
Yes.
Do you know any models which illustrate kind of quantum speed up in a sense that you would have, you would be getting stuck classically, but quantum mechanics would save the day and, give you much faster relaxation?
I get that. That's in principle do. I would need to think how to. Yeah. No, it's a good point.
Another very late question: any links to gauge theories regarding to because there is a constraint always figuring out here.
That's more connected to point 3 that I didn't go into. So this and I won't give you a full answer, but plaquette models are plaquettes where you just have interactions between spins, multi-spin interactions with normal dynamics where you flip spins by one, no explicit constraints, and they have a dual description in terms of excitations, plaquette excitations, where the dynamics, because the transformation is non-linear, is effectively constrained. So these are like fractons, what people call fractons, but classical. In fact, fractons emerge from there, actually. Well, no. Not the quantum information side of things, but this paper by Claudio Chamon in 2005 is a quantum version of a model of that kind. So that's a bit more connected. But those are problems where the constraints you don't put by hand, they emerge, effectively.
So I have a question about this dynamical heterogeneity.
Yeah.
So that if I look at this system at any given time, I have some sort of distribution of the sizes of these regions that have relaxed.
Yes.
So is there something universal one can say about the distribution and how it evolves in time, either in the classical case or in the quantum one?
So in the classical case, it relates to a picture that's gone. I said that imagine you are in equilibrium, you have these trajectories that are very rich, and so these trajectories are fluctuations of your spins going up and down, and they have this this pronounced space-time fluctuation, in the sense that if you have a fluctuation where all the spins get killed, it takes very, very long time to create the spins. And this is essentially kind of the physics of what's going on here. So now I said that this is a manifestation of an underlying first-order transition where there are two phases. One phase that is essentially, the one you're seeing, and one phase which is empty. So this is liquid vapor physics, qualitatively, in the sense it's a first-order transition between two phases not related by symmetry. One phase which is dense, and another phase which is, empty, the liquid and the vapor. And if you have liquid vapor physics, several things happen. Of course, you can have macroscopic interfaces if you prepare the system at coexistence. But if you're close to, if you're not at coexistence but close in the liquid phase, you have, bubbles of vapor. And these things are bubbles of, are essentially bubbles of inactivity in trajectories. So what I'm trying to say is that the properties of those fluctuations are determined by the first order transition point nearby. Okay? So, and then depending on the specific problem, it's the same kind of physics. You have, so you have interfaces, and the interface has fluctuations, and there's some surface tension, and the surface tension should be the same in the bubbles as in the, so the properties of the surface tension should be the same as the one that controls the bubbles, as the one that controls, that trajectory, that's kind of the spreading, which was, essentially a flat fluctuating interface. And depending on the model, you can just put numbers into them. I'm trying to answer to you, it's the underlying first order in trajectory space character of these constraint dynamics in general determines the properties, the qualitative properties of these fluctuations in the trajectories. And there is a lot of years of work on just specific problems.
Maybe one last question, Kurt.
Yeah, can you go back to the curve of the autocorrelation function? Yeah, so you spoke about the pairs diffusing.
Yeah.
Were you like? Do you mean that they're diffusing, or you meant that they obey the diffusion equation, right?
So.
Or were you just saying they're moving around?
No, they should diffuse, and.
But then if I look at those curves, shouldn't I see a bunch of like one of a square root t, so on the scales that's a log linear, so.
Oh, okay.
Like
so. No, because if you have diffusing excitations, let's see if we are talking about the same thing. Imagine you have a system where you have diffusing excitations, just diffusing particles.
Yeah.
And the relaxation depends on the particle coming to you.
Yeah.
So what really matters is what's the diffusion constant and the typical distance they have to travel. So one thing is you have a single one covering everything, and another one is you have a finite density.
Yeah.
So the case with finite density decays exponentially with a rate that's given by the diffusion. So in this particular case, there is a composite hybridization of this object.
Yes.
That second order that gives you lambda squared, and that's the thing that diffuses. Okay. So I expect this one to be exponential with something that has to do with the diffusion rate. Because there is in any typical configuration you start from, you will have some non-zero density of those guys.
Yeah. Whereas I was just thinking about maybe.
Yeah, you're thinking of the extreme case. Remember this extreme box in state space. There are these extreme states which are very hard to relax, and those are the ones that have distances which grow with system size.
That's about a appropriate place to close, so let's thank Svante again for the
Thanks.